We already talked about how Starship could be modified in order to overcome the detrimental effects of zero-G onto the human body. So today, we want to focus on another big problem for human spaceflight: cosmic rays.
So what are cosmic rays and why are they so dangerous for humans on long-duration space flights? And of course, how could we modify Starship in order to increase protection against the adverse effects of cosmic rays? Well, let's find out.
There is strong evidence that cosmic rays are really not good for the human body. Just when you thought that weightlessness is the biggest health threat to long-duration missions, such as a voyage to Mars with Starship, cosmic rays make it even worse. In our last video, we presented some straightforward and simple solutions to overcome the detrimental effects of zero-G. But cosmic rays are far more difficult to protect against. Cosmic rays are extremely highly energetic particles from interstellar and intergalactic space. They consist mostly of protons, but also atomic nuclei such as helium cores, which are also called alpha particles. This is not to be confused with solar wind, by the way. Solar wind also mainly consists of protons and alpha particles. However, the protons in solar wind have a much lower energy than the protons in cosmic rays. If we compare the flux versus energy for solar wind on the left and for cosmic rays on the right, we see that cosmic rays can reach maximum energies of insane 10 to the 19 electron volts. 1 electron volt, by the way, is the kinetic energy an electron would get when being accelerated in an electric field of 1 volt.
It is a very small energy and therefore often used in particle physics compared to the normal unit we know, namely joule. In fact, 1 electron volt is only 1.6 times 10 to the minus 19 joule. We see that the most energetic cosmic rays have kinetic energies of up to 1 joule, which is just totally insane. Such a particle would hit you with the same energy as a golf ball being dropped from a bit over 2 meters of height. That's absolutely crazy. Compare that to the solar wind, where the highest energies top off at around 1 gigaelectron volts, so 1 billion times weaker than cosmic rays. Now, protection against the solar wind is actually not so hard. There's always solar wind, by the way, however it only gets dangerous during coronal mass ejections, so when a solar storm happens. Then the flux is drastically increased. For that purpose, Starship will have a solar storm shelter. Elon has mentioned this quite on numerous occasions. It will consist of a double-walled chamber, probably filled with water, because water is an excellent radiation absorber. However, the shelter will have to be quite small in order not to be too heavy. So the crew of Starship cannot spend the whole time in the shelter. It will be too small to be permanently occupied and only used during solar storms.
But cosmic rays come constantly, all the time, from all directions. And because they have such high energies, they are much more dangerous than the solar wind. Some recent studies, link in the description, go as far as to say that cosmic rays could lead to long-lasting brain damage. Because if such a high-energy cosmic ray hits the hull of Starship, it would create a secondary cascade of high-energy neutrons, which would hit the brain of our future Mars settlers in Starship and lead to long-lasting detrimental neurological effects, such as memory impairment and anxiety. This is not 100% proven yet. More research will be needed, but it's safe to say that even if there won't be any permanent brain damage, certainly there will be DNA damage. And we all know that this results in a highly increased risk for cancer. So then what can be done? Well, fortunately there are some solutions.
1. Cut down travel time. Okay, this is of course the most obvious one, because the total amount of radiation our Mars settlers receive is of course proportional to the time spent on the voyage to Mars. A trip half as long would mean half the radiation dosage. We know that Starship uses chemical propulsion. A trip to Mars with this propulsion method would take roughly around 6 months. However, there are possible different propulsion methods which we will analyze in a separate video, because this topic is so extensive in itself. Possible propulsion methods would be nuclear thermal propulsion, which could cut travel time down in half, some form of ion drives, Hall thrusters, and of course the famous Bessemer drive, which could cut travel time down to 30 days. That would be of course ideal. Of course, each comes with pros and cons, as you can imagine, but more on that in a future video.
2. Anti-radiation supplements. Now, the usual anti-radiation supplements, such as potassium iodide, cesium, or strontium, don't work here, because we are not talking about the radiation as, for example, in a nuclear fallout, since cosmic rays directly damage the biological tissues in the human body. However, there is research indicating that a supplement called PLX 5622 could significantly reduce the adverse effects of cosmic rays. Link in the description. This new substance is currently in clinical trials, and hopefully soon we can find out if supplements can help to reduce the harmful effects of cosmic rays.
3. Shielding Starship with water. We know, as we have mentioned before with the solar storm shelter, that water would be indeed a very good absorber of radiation. So then we might say, okay, therefore let's just shield the entire crew section of Starship with a water shield. Now let's do a quick calculation how much water would actually be needed. Now, to have efficient shielding, some papers suggest that the water barrier should be at least half a meter thick. We know that the crew section of Starship takes up about 40% of the volume of Starship, with 60% being the fuel tanks. Let's approximate the crew section as a cylinder, so a cylinder with a height of 20 meters and a diameter of 8 meters. The total diameter of Starship is 9 meters, so let's idealistically say that we can use the full 1 meter difference for water shielding. And let's say that we can use the full 20 meters height for the surrounding water. That would leave us with a height of 19 meters for the crew section. We would then get the needed water volume of 317 cubic meters. Now, with a density of water of 1 gram per cubic centimeter, which corresponds to 1 metric ton per cubic meter, we then find that the water would weigh 317 metric tons. This is a lot more than the Starship target dry mass, which Elon said should be no more than 120 metric tons in the future. The propellant, by the way, weighs 1,200 metric tons. So propellant plus Starship mass would be 1,320 metric tons. Therefore, the water shielding would increase the total weight by 24%, which is quite a lot. And apart from the big weight increase, of course, the reduced stability of the outer Starship hull would be a severe issue.
4. Shielding Starship with nanotubes. What if there would be a very light material with excellent radiation absorbing characteristics, while being strong at the same time, and that's even increasing the strength of Starship's hull, namely boron nitride nanotubes? It has been under investigation at NASA for quite some time now, as the most promising material to shield against cosmic rays. The boron atoms can capture neutrons very well, and therefore would be ideal to capture those secondary high-energy neutrons created when cosmic rays hit the hull of Starship. Newer research from NASA's Langley Research Center shows that the boron nitride nanotubes can be even enriched with hydrogen, because the proton of the hydrogen atom can best absorb the energy of the secondary high-energy neutrons. Furthermore, these nanotubes are extremely strong, as such a material would exhibit a very high yield strength, almost as high as carbon nanotubes, which are 100 times stronger than steel. But HBNNTs would be able to resist heat much better than CNTs, namely up to temperatures of 900 degrees Celsius, compared to 400 degrees Celsius for CNTs. The Australian technology company PPK signed a joint venture agreement with Deakin in November 2018, with the goal of manufacturing BNNTs on a commercial basis, which is excellent because they could mass produce the shielding needed for Starship. we found a paper where some calculations for the required thickness of HBNNT shieldings are performed. Link in the description, of course. And they came to the conclusion that a 30 cm thick shield could reduce the radiation dosage to safe levels. HBNNTs have a density of around 1.4 grams per cubic centimeter. So in our Starship example, as in the case of water shielding, we would get a total mass of 239 metric tons. Certainly already better than water and much more practical, but still much too high.
5. A combination solution. A nuclear thermal powered Starship, as we said before, would cut down travel time by about 50%. Therefore, half the shielding thickness of HBNNT shielding would suffice. But now let's assume that the PLX5622 supplement shows good results in clinical studies, possibly reducing the received damage from radiation by another 50%. We then could make do with an HBNNT shielding thickness of 10 centimeters instead of 30 centimeters. Therefore, we could have a mass of 60 metric tons for the shielding. Still a lot, but already much better. Now let's assume that Elon can really bring down Starship mass to 100 metric tons. So we would then get a total Starship dry mass of the Starship itself plus the shielding of 160 metric tons. This should work. Even more so, since in this scenario Starship would be powered by nuclear thermal engines, which would reduce the weight of the propellant, so that the Starship mass with propellant would still be less than currently with chemical propellant. So we think that a combination of cutting down travel time with nuclear thermal propulsion and additional HBNNT shielding and the use of anti-radiation supplements such as PLX5622 will be the ideal solution for flights to Mars. And we of course can combine this with solutions for the other problems, such as for example solving the low gravity problem, so that we can then dock this whole modified Starship with a rotating Bigelow habitation ring to also solve our zero gravity problem at the same time.
Oh, and as for the radiation on the surface of Mars, our friend Angry Astronaut has made a really good video on that topic, which you should definitely check out. Link in the description. And we also encourage you to subscribe to his channel because he's awesome, and believe it or not, he rants even more than we do.
So what do you think? Which solution to solve this problem is the best one? Is a combination solution maybe the best one?
And if you think that we missed any solutions, be sure to tell us in the comments.
So you just watched the JS Space Report, which we do every Monday and every Friday. On Monday we give you the most recent news and developments in spaceflight, and on Friday we answer some interesting questions about spaceflight and space-related topics.
So thanks for watching, and I would say, on to the future!
And on Fridays we talk about more general topics where we explain certain concepts.
Jay.
It's so long every time, I don't like it.
So I can say it.
No, but it's too long. I don't want to say it every time, the whole thing. Technologies with a strong emphasis on human space flight